transition now into a presentation by Giselle Aviles. She worked with Renato Navarro, who is at Stanford University. Giselle is majoring in bioengineering and returning to Foothill in the fall. She's a big fan of strawberry milk. Her lab partner, Isabel, who we're going to hear from next, introduced her to, or reintroduced you to it, and it's fantastic. So many people should try that. And the title of Giselle's talk is How Can Help Help? Oh no, that is not the right one. It's the title here, Engineered Protein Hydrogels for Three-Dimensional Printing in Cell Culture. So Giselle, take it over.
Hi, everybody. I'm Giselle, and this summer I had the opportunity to be at the Hydrozone Lab located at Stanford. I was mentored by Dr. Renato Navarro. Thank you so much, Sam, for being an amazing mentor this summer. And yeah, like Sophia mentioned earlier, my title is Engineered Protein Hydrogels for Three-Dimensional Printing and Cell Culture. It's a bit of a mouthful, but I promise we'll get through it. So overall, the motivation of this project, I want you to think of cells as teenagers. They need a place to adapt. They need to have enough room in their surrounding environment. Otherwise, not all of us can be doctors. And recent studies suggest that this is not only a necessity for their survival, but their overall proliferation. Cells are also really expensive, so we want to make sure that we have the best shot while we have them. So this made a just overall question for scientists like Sam to want to create a flexible material for studies that have any sort of things to do with tissue engineering as well as regenerative medicine that have to do with not only cell seeding, but cell encapsulation. So how did we do this? I want you to think about dynamic chemistry. Now, a lot of us have been exposed to dynamic chemistry, but haven't necessarily thought about it in the sense of dynamic chemistry. So I want you to think of ionic or even hydrogen bonds. As you may or may not know, they have an on-off rate, which means that they stay together, but they also break apart constantly. This is not only predictable, but it allows for us to use this breakability, this on-off rate, for the cell's remodelability. So as I mentioned earlier, cells are like teenagers, they want space. So the cells use this predictable bonding of the breaking to grow themselves out. It also provides the gel with its visco-like properties. It works to mimic the same stress relaxation environment seen in the natural cellular environment. Now, that was a lot. So what I mean by that is tissues, you want to put the cells around the same environment as the tissues that they came from. So we do this by using a test called stress relaxation, which I will go into more detail in a later slide. So in a deeper look into dynamic chemistry, I'm going to talk about the hydrozone bond that we use. So we use one hydrozone bond. As I mentioned earlier, it has dynamic chemistry, so it has a predictability on and off rate. It's either HA aldehyde or HA benzaldehyde, HA being hyaluronic acid. In the health gel, there's hyaluronic acid and elastin-like protein. So on the elastin-like protein, there is a hydrazine. The hydrazine can either bond to the aldehyde or the benzaldehyde. The reason I bring this up is because the aldehyde, when bonded to the hydrazine, has a stress relaxation rate that matches the tissue samples a lot better than the benzaldehyde, as seen on the graph on the right. However, the aldehyde only stays around for 2 to 3 days versus the benzaldehyde stays for a much longer period of time. So then this created a new question. Could we make a gel that matches the cellular environments seen in human tissue by adjusting the mechanical properties? This not only touched on cell remodelability, but also shear thinning, which is the tissues that I was mentioning earlier, matching the tissue samples to the gel itself, as well as controlled erosion. We don't want that aldehyde leaving before we get a chance to actually modify anything to do with it. So what I did was material synthesis and material characterization. So when I say material characterization, that sounds really fancy, but what I mean is just I tried not to break this really fancy and expensive machine. So synthesis of hyaluronic acid modified with aldehyde, it's essentially just adding, so we do a lot of mediation through EDC, we add an alkyne and we get an aldehyde. And then over here on the right, you can see a and NMR. I don't know if you guys are familiar with that, but as someone previously said, these nice squiggly lines are a depiction of peaks of aldehyde. So that's how we can tell a normal hyaluronic acid strand versus a modified hyaluronic acid strand. And on the next slide, you can even see the ELP hydrazine Bach. So a Bach group is what we use to, it's essentially a filler. And remember, we use hyaluronic acid and ELP. The H is the H in help, and then the ELP is the ELP in help. And this is all to make the gel. And then the Bach, again, is the filler. The ELP hydrazine is the bond that we used earlier for the aldehyde. And then NMR again. So then you're like, Giselle, this is a lot of synthesis. Not gonna lie, I'm a little flustered. So now we're gonna go into the stress relaxation. You're like, Giselle, you mentioned this earlier, but now I'm thinking about synthesis. So we're gonna slow it down. We're gonna go back to tissues, back to where it relates to you. So as I mentioned earlier, tissue to tissue, you need to make sure that cell is comfortable in its environment. And the way that we test that is through rheology. And an example of that is this graph. So we want to make sure that the tissue that we tested on matches the same exact, the gel matches the same exact tissue sample that came from. And this graph is basically that. And then where this can possibly be taken or where it can be used. So these are some cardiomyocytes that have been encapsulated in the material that we were working on, that not only demonstrate a unique phenotype, so meaning that the cells themselves stretch themselves out in a way, stretch themselves out in a way that we normally wouldn't see, which is really cool, as well as some extrudability, meaning we just push the gel through a needle, a 31 gauge needle, which highlights the 3D application potential. And in conclusion, a new hydrogel was developed using dynamic bonds, and it was matched to a similar stress relaxation, and a variety of applications using 3D printing as well as cell encapsulation were used. And these are my acknowledgements. Thank you so much to the SLI and Steve and Marissa, and thank you so much, Sam. You were a great mentor, and Lucia as well. And I'm so excited to be staying.